Alright. What about?
Yes, sir.
We are.
Yes, sir. What we're here.
Yeah, man. We have some unfinished business about assessment. On a meet and deal with it.
Yeah.
You hear me?
Yeah.
Yes, sir. I saw it. What's the person that proposed like
Huh?
Yes, sir. Yes.
So you start out the assessment thing?
Yes, sir. We did sort it out.
So what you guys proposal?
3 assignment, 1 test, and the final, sir.
Let's say assignment.
70-30. 70-30. 3 assignments, sir, and then the finals. So 3 assignments, 70% coursework, and then the finals. The multiple choice finals, where I say I'll give it.
Then they something the midterm not test though. So 2 assignment, 2 tests.
Alright then.
Understand?
Yeah.
2 assignment, 1 test.
Yeah, man, that can work, sir. Yeah, man.
2 assignment, 2 tests. 2 tests are homework. Multiple choice.
Alright. So,
yeah, man. So the coursework could have been 70% and the final would have been 30.
Yeah. So the 2 assignment is 2 assignment. How will we do that now? 2 assignment, 20% each.
Yeah. And then one mid semester would have be 20.
30 and the final 30.
Yeah.
it's 2 mid semester, sir.
Huh?
Like you just say one mid semester, but we have to have 2 mid semester, 2 mid semester test, is it? 2 assignment.
No, man, two assignment, man.
You know, I hear properly. Sir said 2 assignment and 2 tests and the final exam.
No.
No, man. Two assignment, 1 mid semester, and a finals. That's why I said 2 tests.
Yeah.
2 tests them split in a mid semester and final.
Alright.
Alright.
Alright, sir.
Alright, so we are agree on that now, sir.
Yeah.
Yes, sir.
So let's go back and clear up dot product and cross product. You see that screen?
No.
You answer the screen?
Sir. What? No, sir. What?
No, I'm gonna share it, man.
No, I see it, sir.
Hold on, man. Where the backside, man? Let's see. You seeing that screen? Not seeing that either.
No, sir. Not as it, sir. Sir, when you ask us to say, I would take a long time to respond, it's because we have to touch the screen. All right, sir? It's no disrespect to you.
Cool.
Yes, sir.
But yes, you know, man. I'll lose this thing. So so Dre, what am I doing wrong, you know? Because I'm gonna bring up the screen. I'm gonna say share screen. Are you have to say share screen, you know? Dre.
Yeah, yes, sir.
Are you? What am I doing wrong? Because I don't mean to share my screen. Are you have to share your screen? I saw how you go.
Sir, wait. You know, it's an option to share the screen.
Yeah, I'm going to share it.
Sir, you have to click on it, you know, sir. You have to click on the screen that you want to share.
I'm going to click
But
on it.
You click the share screen and then there's on the right bottom right hand corner, there's a next thing I have to click to share as well.
I don't know. I don't feel dumb to write it.
Sir, the screen
Turn over about it, man.
It's open.
May I have the screen open?
All right, so on the bottom of this your computer screen in a Zoom, you're supposed to share screen, right? When you click share screen, you see a little window pop open. When that open, the screen that you want to share, just click on it, and then on the bottom right hand corner of that screen that pop open, you see share. You just click on it. Share.
Now if I go back to the Zoom screen.
Yes, sir.
All right. So I'm back to the Zoom screen.
Back to the Zoom screen, beside record and chat is share screen.
It's the share screen, but it
all right. So click on the share screen now. When you click on that, the next thing that's supposed to pop open.
No, but it peel out. I don't know why it peel out. Oh. Like me share screen already. I'm going to click on it already, you know.
Oh, you see something says stop share?
You see something that says return to me. I'm going to share screen again. Share screen. You still not know?
Still not, sir.
No, sir.
Still not.
They started sharing.
All right, sir.
You see it now? All right. Yeah. I see dot product and cross product, right?
Yes, sir.
Just maximize the screen.
I maximize that.
Yeah, you would have done, sir.
You're good, yes or no?
Yes, sir.
Yes, sir.
All right.
Great. Sorry, recording.
Yes.
Good.
So we have two vectors, right? Vector A. We have vector A, which is AX, unit vector AX, AY, unit vector AY. That means this vector AX, AY, AZ is in the Cartesian coordinate system, right? And we have BX, vector B is BX, BY, BZ. So X, direction X, Y, and Z are orthogonal to each other. So unit vector AX is at right angle to AY and AZ. Unit vector AY is at right angle to AX and AZ. And unit vector AZ is at right angle to AY and AX. All right. Similar for vector B. bx, by, and bz. And it's in the ax, ay, az direction. No, not written here, is the definition of dot product. The definition of dot product is for two vector A and B is the modulus of vector A times the modulus of vector B times cosine of the angle between them. Now let us do this little algebra now. We have vector A broken down into ax, ay, az. Cosine of 90 is what? Question for you to answer. What's the cosine of 90?
Yes, sir.
0.
So if they are at right angle to each other, A times B times cosine of the angle between them would be 0, right?
Yes, sir.
Yes, sir.
Would be. And if they are parallel to each other, the angle between them would be 0. So cosine of 0 is 1, right?
Yeah.
All right. So just let's do this little maths now. AX dot BX would be the magnitude of AX and the magnitude of BX times cosine of the angle between them. And they are parallel to each other, so cosine of 0 would be 1. So AX dot BX would be just AX times BX, right?
Yes, sir.
Agree?
Yes,
So
sir.
AX dot BX would be AX BX. AX B AY dot BX, the angle between that would be 90. Because in the AY and AX are 90 degrees to each other. So AY dot BX would work out to 0 because the cosine of the angle is 0, right?
Yes, sir.
With me? AZ dot BX would work out to what?
0. 0, sir.
Because the angle is 90. Now, AX dot BY is what? What that works?
0 again, sir.
AY dot BY would work out to what?
AY, BY, because them parallel.
Right. And AY dot BZ work out to what?
0.
0.
And we go to the Z. And you get the picture. So AX, A vector A dot B is AX BX plus AY BY plus AZ.
Oh, you have C out this, sir.
Mistake.
Oh.
It should be BZ. All right.
Yes, sir.
Now, cross product. Cross product of two vectors, A and B. Oh, before we move, you notice that A dot B result in a scalar. You notice?
Yes, sir.
So A dot B is called the scalar product of a vector. The cross product of two vectors A and B, written as A cross B, is a vector quantity whose magnitude is the area of the parallelogram formed by the two vectors. So then, if we look at these two vectors here, A and B would form a this is, ignore this, would form a parallelogram by putting B here and A here, right? You with me?
Yes, sir. Yes, sir. We're with you. We're press the button, sir.
Yeah, would form a parallelogram by doing this. Bam, bam, right? So A cross B is the area of the parallelogram formed by A and B. Now, A cross B, taken in a similar way as we take these two vectors A and B, the cross product, taking each term, term by term, right? In other words, AX cross BX, AX cross BY, AX cross BZ, and do the same thing now. If we group the terms, so we are going to end up with what? 1, 2, 3. We are going to end up with 9 terms, right? If we group them, we can put it in the form of a matrix, looking like this, right? So these are the unit vector AX, AY, AZ, and this is AX, BX. This is vector A, and this is vector B. That's simply just taking each term, that is AX, vector AX, right? AX unit vector AX cross BX unit vector AX. So we will get, if we group that, what we end up with is this matrix, right? So if you should just work it out there, right? Let's do this matrix. How you do matrix? You take this vector AX, you bracket, that is AX BX minus BY AY, right? BY AZ. You remember how to do matrix?
Yes, sir. And the determinant.
Yes, determinant, yeah. So if you do that determinant, all the term that you would get by going this the long way, you would get it the same way here. All right? So then, with that said, That said, then we can go and do some examples. Yeah. All right. So today is supposed to be tutorial. So this is our first tutorial. Let us do a few examples. First, going back, we have a vector P1, 2, 3 meter. So here you are, P at this point, P, x equal 1, y equal 2, z equal 3. So you go.
Yes, sir.
And Q, x equal 2, y equal -2. How come like this? Oh yeah, and z equal 1 here. So x equal 2, y equal -2, and z equal 1.
-1, sir.
So vector PQ, that is the vector from P to Q. Vector PQ would be the vector from P to Q. So Q is your final destination, right? The vector starts at P and ends at Q. So vector PQ would be your point Q minus your point P. Clear?
Yes, sir.
Yes.
So all you would do then would minus your x from Q from your x from P, your y from Q minus your y from P, your z from Q minus your z from P. So this would work out to what? xq minus xp in the ax direction, 2 minus 1 ax, minus 2 minus 2 ay, minus 1 minus 3 az. So this would give you ax, which of course this is wrong. Wait, no. Yeah. This should be
-4.
-4.
No. Q is 1, so this should be, it should have a +1 here. This should not be minus, this should be plus.
Oh.
So it's -2, this is correct. Everybody with me?
Yeah.
Yes, sir.
Now, this one, given a vector from origin G, 2, -1, -1. Okay. So all this is saying, what we are trying to do here is find out the magnitude of the vector and the unit vector. So here we have a vector. Obtain unit vector from the origin of G equal this. So G is at some point out here, x equal to y equal minus 2, z equal minus 1. So from the origin, so that vector would be x minus 0 in the ax, y minus 0 in the ay, z minus 0 in the az. So it will be 2ax minus 2ay minus 1az, right?
Yes, sir.
So based upon our definition for unit vector would be vector G, which is this, over the modulus of G. The modulus of G would be the square root of 2 square plus minus 2 square plus minus 1 square. That equals 3. Agree? One more, am I listening?
Could you say that again?
Yeah, man, we agree.
Sir, is
Yes,
that
sir. That's three, sir.
Huh?
So what is the first term under the square root?
2.
2 square.
2 square.
2 square
2 square.
minus 2 square minus 1 square.
So it's the square root of that. Square root of 2 square plus minus 2 square plus minus 1 square, which equals 3. Right? So the unit vector would be G, vector G
Divided by the mod.
divided by the modulus. So this divided by 3 gives 0.667 AX minus 0.667 AY minus 0.333 AZ. All on board?
Yeah, man.
Yes, sir.
No,
Yes,
sir.
sir.
But then 0.6.
Huh?
And 0.6 of the compromise.
2 divided by the term in front of the ax divided 2 divided by 3.
2 divided by, I get it. So
Yeah.
2 is G, 2 is G, and 3 is
Modulus of G.
Everybody get it now?
Yes, sir.
Yes, sir.
Now, vector A equal 2ax minus 3ay plus az. Vector B equal minus 4ax minus 2ay plus 5az. Find A dot B. So A dot B is what?
The modulus of A times the modulus of B. Cosine the angle between them.
Right. And it's also what? AX times BX plus AY times BY plus AZ times BZ.
All right, sir.
Right? In other
Yes, sir.
words, in other words, mhm. Where you want the clarity? Tell me. In other words, right? If you work it out, right? If you say AX dot with AX, right? AX dot with vector B, you would get the modulus of A. Now you would get AX times BX.
Sir,
Oi.
the meeting gonna stop. So let's just end it and restart it, but just join back with the same link.
All right, cool.
Sir, your mic is off.
All right, you hear me now?
Yes, sir.
Yes, sir. Ian.
Okay, good. Are you seeing the screen?
Yes, sir.
Yes, sir.
Okay. So where we were here, A dot B. So look at this now. AX, which is 2AX dot the entire B. So 2AX dot minus 4AX.
Sir, wait. Oh, no, man. Never mind, just started. Oh, good. Cool, sir. Continue.
2AX dot minus 4AX would give you 8 because the angle between AX and AX is 0 and cosine of 0 is 1. Agree?
Yes, sir.
So that would be minus 8. Now 2AX dot minus 2AY, the angle between AX and AY is 90, so that is going to work out to 0. 2AX dot 5AZ, angle between that is 90, so that is going to work out to 0. And the same thing if you dot minus 3AY with B, between AY and AX is going to be 90, and between AY and AZ is going to be 90. So this is going to work out to just minus 3 times minus 2. So that's why it works out to minus 8 plus 6 plus 5, which is 3. So A dot B is 3.
Sir, in the notes part we have since ax dot ax equal a, it should be equal 1, and then the other part, the ax ay equal 0.
Right. Remember the definition of the dot product. The dot product is is A times B times cosine of the angle between them. Right? A dot B is the modulus of A times the modulus of B times the angle between them, right?
Yes, sir.
Times cosine of the angle between them. A dot B is A times B times cosine of the angle between them, right?
Yes.
So I'm saying you have the vector A, which is 2ax minus 2ay plus az. And you have the vector B, which is minus 4ax minus 2ay plus 5az.
Yes, sir.
You note that ax, ay, and az are orthogonal to each other. So ax is at right angle to ay, which is at right angle to az. So when you have these two vectors, when you dot ax with ax here, so you're expanding it out into its nine portions. You would have ax dot ax, ax dot ay, ax dot az, and then you come ax dot bx, ax dot by, and ax dot bz. You would again have ay dot in the three of these, right?
Yes, sir.
And you would have az dot in the three of these. I'm saying the only ones that not gonna come out to 0 is when you dot ax here with bx in the ax in direction, because these are parallel to each other. All others are orthogonal.
Yes, sir.
So you would work out to merely 2 times minus 4 plus minus 3 times minus 2 plus 1 times 5, which works out to 3. Here it is. Ax dot ax equal ay dot ay equal a. All of those are 0. The angle are 0. So cosine of that is 1. All right. The cross product now, which amounts to just simply the determinant. So how this gonna? What you do? You blank out this one, you take out this and this. So ax would be minus 3 times 5, which is 15, which is minus 15, minus 2, which is 13 AX. Follow that?
Yes, sir.
Yes, sir.
And AY now, you take out this. So it would be, that gonna, it would be 1
No, sir.
1
5.
1 times minus 4, which is minus 4, minus 2 times 5, which is minus 10. So that would be
Minus 14.
minus 14. And of course, you have the AY. And for AZ now, you take out this. How that work now? It would be
2 times minus
2 times minus 2, which is 4, minus
4 times minus 3.
that would be minus 4, minus 12. Everybody get it?
Yes, sir.
Yeah, man. Run it again, sir.
You will like? We're doing this determinant.
AX. So AX is
So it,
minus 3 times 5.
yes,
Minus 1 times minus 2.
right. So that gives 13, right?
Yes, sir.
This is minus 15 plus 2, minus 13. This is, when I take out this row, or this column, you would end up with minus 4, minus 10, minus 14. And then you take out this column, so you'd end up with minus 4, minus 12, which is 16. Very comfortable?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, man, good so far.
All right. This one, so now, find the distance.
Sir,
Huh?
when I say why it is negative 14 AY, shouldn't it be positive? Because you're going to have 2 times 10 minus negative 4 times 1. So that will give you a positive 4 and a positive 10.
Yeah, but remember when
Okay,
I have
subtract
find
them.
determinant.
No,
But when I do what?
remember say,
When I find the determinant.
It is minus 4 minus a positive 10. So both of them are ending up with a negative sign. If you have minus 4 minus 10, both of them are ending up with
Watch now. Determinant is AD minus BC. So A would that be the 2 and D would that be the 5. So 2 times 5 you get 10. Then a minus the negative 4 times the 1. You see me? So you're going to minus a negative 4, which are going to give you positive 4. So you're going to be 10 plus 4.
Or is the other way around?
Yeah, but remember the in the matrix setup you have plus minus plus then minus plus minus. That's something that will cross.
Yes.
All
For true.
minus plus.
Yeah, for true. Respect.
Okay. All right. Now, this other one, find the distance between A and B. What the first thing you think about?
Repeat the question.
So the question, find the distance between A and B. If you just black out the solution out of your mind for a minute, you will, of course, realize that this is Cartesian coordinate, right? Because this is cylindrical coordinate. Because the cylindrical coordinate, this is R, right? This is your angle phi, and this is Z. Right? Oh, one thing, let me point out this to you, and I think I told you before, depending on whoever book you take up, for the cylinder, the radius coming out, which I believe when we were explaining it, we use R. This book is using rho, right? So don't get confused by that. So rho, your angle phi, and your distance Z. So rho phi Z, same thing as R phi Z. Okay. Now, okay. I don't believe we had explained this, you know. Okay. Work with this. The conversion Somebody trying to say something? Yeah, but you're very low. Huh? Okay. All right. All right, let me go back to this. The I wanted to see a diagram where it is done, but anyway, this is it. The conversion from Cartesian to cylindrical is as follows. From R, or your vector R rho, whichever one you use. From R rho to X in coordinate in Cartesian. Oh God, hold on there. I must find something better than that. All right, you seeing this?
Yes, sir.
All right. Here is your cylinder superimposed on your Cartesian coordinate. All right. So you have your R, your phi, and your Z. All right. Now look at it now. This is your R. All right. So all this is a right angle triangle. If you do this, all right. So if you want to convert your R in Cartesian to your R in cylindrical to Cartesian, it would be R cos phi. Because all this is a right angle. You don't get it? This. Okay, you're forming. This is your, what they call it, base. This is your hypotenuse. This is this. So this is this cosine this. Because this is a right angle. Remember this is not out to the edge, you know. This is in. So see your right angle there. This is the right angle. This a 90-degree right so. So this would be, or this would be this cosine this. And this would be this sine this. Opposite over hypotenuse. Now remember that?
Yes, sir.
All right. So if we go back to this, we are saying now that you want to find the distance between A and B, but this is in cylindrical. So the first thing you have to do is to convert the coordinates in the cylindrical to Cartesian. Because that's the only way you can find it. So your X in Cartesian is your rho cos theta. And your phi is your rho sine phi. I'm mixing up theta and phi. Rho cos phi, rho sine phi. This is your y. Your z remain the same. So you would first convert these to Cartesian coordinate. Phi is 5/6. Rho is 2. So your x would be 2 cos 5/6. And your y would be 2 sine 5/6. Of course, your z remain the same. All right. So And you convert your B the same way. So,
Sir.
Question?
Pi by 2.
Huh? Say that again.
Sir, the first term after the equal sign, it have 1 cos pi by 6. Shouldn't it be 1 cos pi by 2?
That's B.
Yes, sir. For B, yeah. Should be pi by 2.
Here is B here.
I say the term where the angle, shouldn't it be pi by 2?
Yeah, this angle should be pi by 2, yeah. This one here. This here should be pi by 2. All right. This should be pi by 2. This is correct. And your Z remain the same.
So the book of error.
Most book have error, man. I don't want to bolt and write both chunk. I know that the error in a good way. Alright? So then you could do your A minus B. Or your B minus A. Which you come out with this. And then the modulus of that equal this. All right. All right. This one now is spherical. Again, you have to do the conversion. All right.
Yes, sir.
The spherical coordinates are r, theta, phi. In rectangular system, the x is r sine theta cos phi. And y is r sine theta sine phi. And z is r cos theta. The z is easy to see because it would be like the z would be like the x in the cylindrical. But the others are a little bit more complicated. So you do your conversion for x, y, and z for both vector A and vector B, which would work out to this and this.
But sir, why if it is in the A part, why for the cos, AZ, you have 1 cos? It shouldn't be 0 cos.
Y in the AZ. All right, AZ, this is this. This is what you're talking?
I want for the man. because R is 1.
Okay.
R cos theta. Theta is pi by 4. All right. So you convert A to the Cartesian here and convert B Cartesian. So AB is B minus A, which gives this. All right. And it says,
Oh, sir, lightning a flash. Sir, lightning a flash. I look up Wi-Fi, so yeah.
Lightning a flash. I hold that. I hold us start. Which part you there?
Jordan Adams, sir. I'm just saying that I'm going to leave the class because lightning is flashing and.
All right. Anybody else explain where are you located?
Discovery Base, sir.
Okay,
Same
because
time.
I'm in Mandeville. It's not start yet, but obviously when it start, we have to start. All right. You catch up from whoever remain until we.
The video I go post here, so you can probably follow.
Yeah, okay. All right, good enough. Find the unit vector AB in problem 5. Okay. Modulus of AB. This is it. This is your vector AB here. Unit vector is vector AB over the modulus of AB, which is this. All right. So, all right. I go on to go back to something that we left off last week that we said we needed that product for. So just do a screen dump on these other examples. And then I'm going to switch back to all right. So let me go back to this though. Okay. Divergence theory. Here is the definition for divergence theory. Now let me explain this to you. Remember what the operator del is?
Yes, I don't remember, sir.
The operator then is the partial. If say you have, this is your vector, right? F is your vector. Del is the partial with respect to x of f, the partial with respect to y of f. So del dot f would be partial with respect to x f plus the partial f with respect to y plus the partial f with respect to z. Right?
Yes, sir.
Now, del dot f is defined as f, which is your vector, dot your differential surfaces. Del dot f, by definition, is this. Right? Look at this. Look at this side of your thing. It says the limit. So del dot f equal the limit as your small volume go to 0.
Sir,
Mhm.
you have to go join for ring. I'm gonna end that link out. Cause it'll cut off. So just pause for a second.
All right. All right. You're back?
Yes, sir.
Okay. I can't remember if you unmute my mic. Let me go back to this. All right. So we said the divergence theorem then, right? Del dot f, where f is a vector, is the limit by definition of divergence. The limit as your volume go to 0. So you have remember we said we have what we call it again, the differential volume. Remember we talk about differential length, we talk about differential surface, and we talk about differential volume. So we are saying as your volume tends to 0, del dot f is your integral over your entire surface of f dot ds. You see, this is del dot f dot ds, integral over the surface. So if you're talking about the cube, in this integral with the small circle here means the integral over the surface, right? Divide by your
Yes, sir.
volume. Divide by your volume. So from that, here, del dot F, you move your delta V over here, you integrate over the volume. You're only left with the integral of F dot ds over S. So, first thing first.
Sir,
Slip me.
sir,
Oi,
them two sides mean the same thing. One beside the dot F and the one beside the V.
eh?
Them two sides they mean the same thing.
Which two sides?
One the volume of V, but that we got delta V, and one beside F. That F.
This side and this side?
No, the sign.
This?
Delta sign.
The triangle, sir.
Yeah, the triangle.
Yeah.
The same thing is okay. Right there and upside.
Which one? This and one?
No, man, upper top.
This?
Yes, on the one side I V.
This?
Yeah.
Nah, man. Are two different things then.
So I'm going to tell you, sir, right in this, so I get a little lost.
This is the del operator.
Oh,
When we say partial in a Cartesian, del is partial with respect to x plus partial with respect to y plus partial with respect to z. This now, delta, is a small volume. Delta V is a small volume.
All right, so I got you.
All right. So look again now. Look again, because we are dealing with two things now. We are dealing with surface and volume.
Okay.
Right? So we say this guy theorem, divergence theorem, said this is true. Del dot F equal the limit as delta V go to 0. The integral over the surface F dot ds divided by the volume. And then we move delta V over here, right? So this becomes delta V, well, and change it to dV, which is a small change in V. So if we change delta V to V, in other words, if you integrate something and you differentiate it, I see something again. Sir?
Yes, sir.
Okay. So this come down to this. So here is the verbiage now. You can read that. So you can read this, but when we start, next week when we get into electromagnetics, and we say the divergence of vector F, you know that this is it. gradient. Same del operator. The gradient del gradient is a scalar function. So the gradient, how the gradient differ from this divergence del, you have this unit vector. So the gradient of a scalar del partial respect to x, ax, partial respect to y, ay. So, in other words, if you have a vector, okay, here it is down here. So vector W, gradient of W is partial of W with respect to x, ax, partial of W with respect to y, ay, partial of W with respect to z, az. In other words, you could consider it as the gradient in every direction. So you have the Cartesian, which is the coordinate x, y, and z in the ax, ay, az. So it would be the gradient of your vector in all three directions. And similar for the cylindrical and the spherical. Now, how this is going to be important now? Let's look at that. How this is going to be important now, guys. Every single aspect of electrical engineering, or every specialization in electrical engineering that you can possibly think of has its roots in electromagnetics. Huh?
Power, sir.
Yeah. And as we go along, I'm going to show you how power is the baby for electromagnetics, how electronics is the baby for electromagnetics, how controls is the pregnancy of electromagnetics, and all of that. I will show all of that to you. For example, when we talk about the gradient of, say, a voltage, the gradient of a voltage, in power we say it's 10 volt, but the gradient, really, the gradient, one is at 0 and one is at 12, right? So actually, a 12 volt battery have a gradient of 12. I don't know if you're familiar with like Kirchhoff's current and voltage laws and all of that.
Yes, sir.
They all are derivatives from electromagnetic principles, which I will show to you. All right. And the last one I want to introduce to you is what we call the curl of a vector. And this will be useful again, like when we go to the principles that, like Kirchhoff current law is derived from, our voltage law around a closed path. Curl of F is the limit of delta S and n represent normal, go to 0, as curl of F equal limit delta S n go to 0, the integral around the closed surface of f dot dl. Remember, f is a vector, dl is a vector, over delta S normal. So you can think, when you say delta S normal, you can think of a conductor, right? A conductor, the current flowing through the conductor. If you cut the wire, the surface exposed is the normal surface. So your density, your current density would be the total current going through over that area that you cut, right? Make sense? Yes, sir?
Yeah.
Okay. So delta S normal is that normal surface to the flow of current. And DL would be the length that your current is flowing, and F would be your current. All F and DL are vectors. And the definition for that is this. Del cross F, okay, del cross F equal the curl of F. So del cross F, as we did before when we did the example on curl, on cross product, A cross B, right? So del cross F would be A cross B, and you remember, that's how we get that, which we did in this form, right? And in the cylindrical form, and in the spherical form. Suffice it to say, all of these tables, did you guys pull up Sadiko?
Yes, sir.
You pull up Sadiko if you go on the back, on the cover page, or if you go on the back cover of any electromagnetics book, you will see all of these equations that we try in some way to explain. If you was going to do it, well, I guess I still have to give it to you to do the multiple choice then, but in any test, like you would get all of these equations. the curl, and all of the conversions. So all of that would be given to you. All right. So next week, we are going to start the course. This was just a little crash course in mathematics. So we're going to start Coulomb's law, looking at charge, and then we move on to Coulomb's laws, electric field, different kind of charges, and so on and so forth. So this is what I am asking you to do.
Sir,
Yeah?
I recommend the textbook.
I'm gonna give you that from last week, and in a syllabus, man. And we say Sadiko.
Sadiko?
Yeah, man, the book coming did send another group.
Oh.
Yeah, man, that one there.
All right. So far, you see, I am, I can gauge the face them as to how you guys are observing material. So help me to help you now. And I would like for you to go over the crash mathematics course that we have done so far. Reason being, let me just give you a little heads up. We are going to have 2-point charge, right? Q1 and Q2. And we are going to want to know what kind of force Q1 exert on Q2. Q1 and Q2 exert on Q1. They are vectors, right?
Yes, sir.
So we are going to have to be able to, apart from the equation that we will come up with, our Coulombs came up with, are saying the force of Q1 and Q2, here is a perfect example. F2, which is the force on Q2 due to Q1, is the magnitude of Q1, Q2 times over 4 pi epsilon times the square of the vector between 1 and 2 times the unit vector. Now, this is easy. If you have a vector for Q1 and you have a vector for Q2, you can find the vector between 1 and 2, and you can find the unit vector of that. But you have to know how to do that. That's all the problem is. There is right here to find the vector between Q1 and Q2. So you cannot escape the mathematics that we have done so far and come and do this, which is very easy to do. And it's very frustrating if you don't spend, if you spend the little time now and deal with the little maths up front there. This is a breeze. People say this course is difficult. It's one of the most beautiful courses, and they teach you everything, but you can only learn it if you can find these vectors and these unit vectors.
Yes,
You with
sir.
me?
Yes, sir.
So please, please spend some time on the little maths this weekend.
Yeah, man, we need a plan to put in some work.
Do.
Go over all over do.
Do. You know, help me out for help, you know.
Alright,
But you
sir.
say we find the recording again. In the group or we say again? No.
Them there in our group.
Or the recording, the class is recording.
Yeah,
in the
them
group.
send pan them.
They're in a Google Drive. They're not in the WhatsApp group. The person who had sent the link for the Google Drive, send it back.
What's next then?
Yeah, because we don't like to know we can access it.
Tracy, anytime the class email to you now. Both the WhatsApp and the class email.
We don't have access. Where access to the email?
Oh, yeah.
You have to
Send
send
the
me an
information
email.
there in our group now, please.
Yeah, send the email in our WhatsApp group, and then he will send it to you.
All right.
All right, guys.
Yes, sir.
Yeah.
So next week, Tuesday.
Alright, sir.
Sir.
Alright, sir, no problem.
If you need me outside of that, you can always WhatsApp me or whatever. Or email me.
All right, respect.
That's it.
All right, so I'm gonna check the group for the info.
Yeah, cause we want the recording.
Yeah, one the recording and one. I don't like to practice over there, Max here.
Yeah, cause
No worry about the recording. You said Priya send it up. Priya always send it. Dre, him always send the recording.
Yeah, well, you have to help and all the way verse for this thing, so you have to take time with somebody.
So where is the recording sent?
Just send an email